Hello and thank you for joining us. Geophysics is a big part of what we do here at DUG Technology, but geophysical concepts can be difficult to grasp. In this presentation, I hope to pass on an understanding to geophysics as relevant to DUG. Then I will focus on our latest technological breakthrough, namely elastic multi-parameter FWI imaging. I'll explain what this tech is all about and why it is such a big deal for our company. Drilling oil and gas wells is extremely expensive, not to mention the opportunity cost of a dry well. Therefore, locating wells accurately is of paramount importance, which of course is based on knowledge of the subsurface. Seismic is the method of choice to build a 3D model of the subsurface. The better the seismic, the better the understanding, and better seismic comes from better technology, and DUG's elastic MPFWI is a major step forward. Bats can see exceptionally well, but not with their eyes. They navigate and find food in the dark using sound. Geophysicists use the seismic method to explore for natural resources in a similar way. So what is the seismic method? Put simply, the seismic method uses specialized equipment to make sounds on the surface of the Earth. These sounds travel down into the Earth, and the various echoes that return from the subsurface are recorded. In order to use these echoes, they must first be processed to form a numerical cube of Earth. This processing requires significant compute power and significant specialized mathematical software. It is this processing that DUG does extremely well, having spent the last 20 years building its seismic data processing business along with the associated technologies. Let's now have a look at how seismic data is collected in different environments. Here is a simple cartoon depicting marine seismic acquisition. You can see that both the sound source and receivers are towed behind the boat. The source creates a sound wave which propagates through the Earth. The boundaries between the different rock layers in the subsurface cause echoes or reflections of the sound wave. The receivers are represented by the inverted triangles. In effect, they are special microphones recording the reflected sound waves that return from beneath. While this simple cartoon shows just one source and one streamer, indeed there can be many of both. There can be more than one boat too. Over the course of weeks and months, these seismic vessels can acquire seismic data covering thousands of square kilometres. Here is another cartoon depicting a different type of a marine seismic acquisition, in this case ocean bottom node seismic. The big difference here is that the receivers are no longer towed behind the boat. They are stationary, being positioned on the ocean floor. Our last cartoon depicts land seismic acquisition. This little video shows a simulation of a single seismic source generating a sound wave which propagates through a simple 3D geological model. The model in this case consists of 4 rock layers shown by the different colours. 2 perpendicular cross sections through the model are shown, and the sound source is situated at their intersection. You can see how the sound wave reflects off the interfaces between the rock layers as it propagates through the model. You can also see that even for this simple model, the complexity of the reverberating wave field becomes quite high. It is even more complicated in the real world. Acquisition is just the first step of the seismic data lifecycle. As I have already alluded to, there are a few steps required before seismic data takes a form that is useful for the decision makers. The main high-level steps are shown here. Processing, imaging, and the determination of rock properties are all part of DUG's service offering. Depending on a few variables, such as the size of the survey in question, it may take years before the decision-making can take place. There is always client pressure to shorten the time it takes to get through this series of steps, but conventional processing and imaging takes a lot of time to produce optimal results. Inevitably, there must be compromise to produce results in the time available. Decisions based on the seismic might be, will we drill the well, and if so, where? Or will we relinquish the acreage? As mentioned, the raw seismic data from the field needs work to create a useful product. It needs cleaning and rearranging before we can make sense of it. Imaging is necessary because initially we don't know where the reflections come from. Cleaning up the seismic data is processing. Rearranging the clean seismic data is called imaging, and further mathematical analysis of the clean image data derives rock properties in the traditional workflow. This is a slightly expanded view of Doug's service offerings from slide 9. The reality is that the conventional seismic data workflow is complicated, consisting of many serial steps, many more than are shown here actually, time-consuming, taking many months to years to complete, and involves the subjective testing of parameters. And additionally, many of the steps make simplifications and/or assumptions so that the project can be completed within the desired time frame. Let's now have a look at just one of the processing steps in a little more detail, the step called demultiple. As shown in the little video of the synthetic source on slide 8, the propagating sound wave can become very complicated as it reverberates between all the different layers. All these reflections ultimately get recorded at the surface by the receivers, but not all these reflections are useful in a conventional processing and imaging workflow. Only primary reflections, those which reflect only once between source and receiver, are useful. Removing all the multiple reflections from the data is a complex step requiring a lot of testing, a lot of compute, and an element of subjectivity. Jumping ahead a little, this is just one of the reasons why our MP-FWI technology produces superior results in shorter timeframes. It naturally uses both primary and multiple reflections as signal. What was noise is now signal. Each rock layer has different physical properties. The boundaries between the layers cause sound wave reflections. Mapping these boundaries is structural interpretation. The reflection amplitude is a function of how the properties change across a layer boundary. Rock properties are traditionally derived using specific mathematical algorithms after processing and imaging. Is there a better way? Yes, there is. Based on superior physics, FWI delivers unsurpassed results with rapid turnaround times. FWI requires both sophisticated software and hardware. Doug has invested over a decade of R&D to realise this opportunity. So what is FWI? At a high level, what FWI does is quite simple. It iteratively updates an initial model of the Earth by replicating the seismic experiment inside a supercomputer and then comparing the resultant synthetic seismic data to the raw seismic field data. It keeps updating the Earth model until the synthetic data that it produces matches the field data that was acquired in the real world. In other words, I can have two seismic data sets, the real seismic, which was acquired in the field, and the synthetic seismic data, which was shot over a rock property model, a model of the Earth, on a supercomputer. By comparing the seismic data sets, an update to the rock property model can be derived. The synthetic seismic data is then reshot and the process continues until the two data sets match, at which point the rock property model is deemed accurate. FWI comes in more than a few flavours, and some are certainly tastier than others, so it is important to understand what all these different terms mean. We need to learn the lingo, so to speak. During the second half of this talk, I will explain a little more about some of the important aspects of FWI and why what we are doing at Doug differentiates us from the rest of the pack. To start with, there is a big difference between FWI and FWI imaging. FWI has been used as one of the steps in the traditional workflow for many years now. It has been used as a model building tool prior to imaging with conventional techniques. FWI imaging is something quite different. It attempts to replace the conventional workflow in its entirety, both processing and imaging. It represents a fundamental shift in how we go about processing seismic data. Let's now have a look at the different types of FWI imaging. FWI imaging can be divided into two distinct groups based on the complexity of the Earth model that is updated. The Earth model that we build can be more or less realistic. It can be made of just one parameter, which is very much less realistic, or it can be made of many parameters, which is much more realistic. There are three fundamental Earth model properties that influence the propagation of sound waves. These are the speed of two different types of sound in, as well as the density of the rocks. These fundamental properties are affected by many related rock properties such as rock type, fluid content, porosity, depth of burial, fractures, and so forth. The reflectivity, the loudness of the reflected echoes, is a function of all three fundamental properties. There are two main types of sound waves. They are distinguished by how the sound wave propagates through the rocks. They are known as P waves, or compression waves, and S waves, or shear waves. You can see the difference between the two in these cartoon animations. P waves travel via a change in pressure, like a slinky spring expanding and contracting. Indeed, my voice is travelling to your ears right now via a P wave through the air. S waves travel via a change in displacement, like flicking a skipping rope. S waves can only travel through solid materials. P waves can travel through both solids and fluids. Now, this is where Mother Nature has decided to make things a little interesting. Each time a sound wave hits an interface between different rock layers, 4 new waves are produced, 2 P waves and 2 S waves. Thus, to understand how loud a given echo is, you must understand the physics of both P and S waves. 1 wave in, 4 waves out. But Mother Nature is only just getting started. For simplicity, I will now call the velocity of P waves Vp, and the velocity of S waves Vs. Ultimately, from a sound wave's perspective, different rock properties will manifest as differences in Vp, Vs and density, and therefore influence the propagation of that sound wave. But to completely define just the Vp, for example, of a sound wave requires several quantities. How it changes as a function of direction, how it changes as a function of location, how it changes as a function of acquisition geometry. A realistic Earth model should account for all of these things. Therefore, an FWI that only inverts for one quantity is not realistic. One quantity cannot capture all the complexity of the Earth. Indeed, when you invert for a single quantity, you end up combining the effects of several properties into a single velocity attribute. So something that is like velocity but is not accurate and therefore cannot be used quantitatively. It is not possible to accurately tease apart the single quantity to obtain the accurate individual properties after the inversion. They can only be separated accurately inside the inversion. Therefore, this approach is not best practice. A multi-parameter inversion, on the other hand, as the name suggests, inverts for many properties simultaneously. They are all considered and updated as part of the Earth model when replicating the seismic experiment inside the computer. all while honouring the superior physical principles embedded in the FWI algorithm. For FWI imaging purposes, a multi-parameter inversion is a necessity. This leads us to a final pair of terms, which also relate to the complexity of the Earth model being used. The two classes of FWI are known as acoustic and elastic implementations. The fundamental difference is the handling of S waves. Acoustic versions ignore shear waves, elastic versions utilise shear waves. While this is just one extra property, it is a significant difference from a number of standpoints. Acoustic MP-FWI imaging is a replacement for traditional processing and imaging only when outputting all the relevant properties. Elastic MP-FWI imaging is a replacement for traditional processing and imaging and rock property derivation. This is because it outputs all three, VP, VS and density, of the fundamental properties of the rock layers. On the left of this table, I show the evolution of Doug's FWI imaging over the last 10 years. The picture I have tried to paint for you up to this point is twofold. Firstly, that elastic MP-FWI imaging is a significant technological advancement capable of producing superior results. Secondly, that developing and running a production elastic MP-FWI imaging solution is completely and utterly non-trivial. It requires significant expertise and experience across multiple disciplines and a significant multi-year R&D investment. Mother Nature is inherently complex. A realistic Earth model must account for many parameters simultaneously. I don't intend to discuss the MP-FWI outputs listed here. Needless to say, these are all combinations and different ways of looking at the three fundamental rock properties and are standard outputs of traditional processing, imaging and rock property derivation. If you can't produce these outputs, then you can't replace traditional workflows. Doug believes it is at least 18 months ahead of its competitors and continues with relentless R&D. As we transition from a conventional processing and imaging workflow through acoustic single-parameter implementations of FWI to finally arrive at our latest elastic multi-parameter FWI imaging solution, we are using a more and more accurate model of the physics of sound wave propagation. That is to say, our multi-parameter Earth model is now more realistic. This means as we move down this list, we are making less simplifications and less assumptions. As we touched on in the earlier part of this presentation, when we talked about primary and multiple reflections, as we move down this list, we also have less data being treated as noise, and therefore more data being treated as useful information. All these factors are the reason why Doug Elastic MP-FWI imaging produces superior results. When comparing what we do at Doug to what some of our competitors are offering, it is important to consider these things. The historical implementations of FWI are acoustic single parameter. Many current implementations of FWI are acoustic single parameter. Implementations of FWI that are nondescript are acoustic single parameter. New acoustic MP-FWI implementations still have significant simplifications. Elastic single parameter FWI solutions have very significant assumptions. Doug's elastic multi-parameter FWI imaging produces amazing results and can output all of the required products needed in an exploration and production campaign. You can't develop your own production-ready FWI technology overnight. It takes a huge amount of R&D spanning the related but distinct fields of geophysical algorithms, high-performance computing, and computer science. Doug's FWI technology is the product of a multi-year, significant and ongoing R&D effort. Which leads us directly back to why elastic MP-FWI imaging is such an important technology. In the oil and gas industry, time is money and uncertainty is costly. A single offshore well can cost as much as $500 million to drill. Elastic MP-FWI imaging solves both issues simultaneously. It delivers better results faster. An earlier, more certain understanding of the Earth means less risk, and is therefore of great value to the decision makers. Our goal has always been to realise a step change in the quality and wall clock turnaround time of seismic data imaging and interpretation solutions. Compared to a conventional workflow, acoustic MPFWI imaging takes about a quarter of the time, from 12 plus months to about 3 months, though every project is different. This time will come down as more projects are completed and the learnings are incorporated. They take about 10% of the labour cost, with about 10 to 15 times more compute. Elastic MPFWI imaging uses 3 to 4 times more compute than the acoustic implementation, but as computers continue to get more powerful, this is anything but a problem. Indeed, this plays into Doug's strengths as an expert HPC provider. As we have just discussed, the big difference with elastic is that S waves are accounted for. This means that elastic MPFWI imaging can solve for both structure, i.e. reflectivity, but also all three of the fundamental rock layer properties that cause the reflectivity amplitudes that we observe in the raw field data. This is one of our first elastic MPFWI imaging results using a dataset from Shell. These two pictures are reflectivity images. On the left, we have the reflectivity from the conventional workflow. On the right, from elastic MPFWI imaging. The large, well-defined areas near the top are actually large bodies of salt. Processing and imaging around salt bodies is notoriously challenging. The differences you can see between these two images are material. The reflectivity on the right is a significantly better result. Doug is the only vendor offering production-ready elastic MPFWI imaging. Doug debuted elastic MPFWI imaging at the Image 24 conference in August to an incredible reception. Very importantly, Shell and Chevron also shared their elastic MPFWI results at Image 24, giving industry validation to the direction Doug has taken. Super majors are adjusting their budgets to allow for elastic MPFWI. Doug has 8 elastic trials underway or completed as of February 25. Doug has also won significant elastic MPFWI projects which have not yet kicked off. Here are just a few client endorsements about our MPFWI imaging technology. We have now completed acoustic projects all over the world in a variety of different geological settings. The technology works. It is adding value to our clients. It has been involved in a number of oil and gas discoveries. An early success was the discovery of the Dorado field on the northwest shelf of Western Australia. I hope that this presentation has given you some more insights into this part of our geophysical technology. Thanks for your time today.